Okay, hi guys. So from this lecture, we'll be starting with the new chapter. So that is called isomerism. Okay, so let me write down the heading: isomerism. Okay, so what is an isomer? Isomerism is just the phenomena of same units of atoms in a compound. So that is not as known as isomerism. So definition in one liner would be phenomena of same units is called isomerism. So we'll look into some of the examples of isomerism, so it would bring more and better clarity to you guys. Okay, so we divide the isomerism into two parts. First is structural isomerism, and the other one is stereoisomerism. Okay, now for what is structural isomerism? Structural isomerism is change in position of atoms, and it does not mean that we will change the spatial arrangement of atoms. So it just means that we are changing the position of atoms, and obviously the IUPAC name would also be getting changed. Okay, so this is just change in position of atoms. This is not a spatial arrangement. Spatial arrangement. We'll talk about what is known as spatial arrangement in stereoisomerism. Okay, for now, if you're not getting the term, um, don't get tensed. We'll be covering it in next few seconds. Not spatial arrangement and change in IUPAC name. Changes in IUPAC names. Okay, and what is stereoisomerism? Stereoisomerism is change in spatial arrangement and same IUPAC name. So this is change in spatial arrangement with same IUPAC name. Okay, now structural isomerism is also known as constitutional isomerism or regioisomerism. So I'm just writing the name in case in exam somebody asks you to draw what are the number of or what are the constitutional isomers of this compound. So you should not get confused that constitutional isomer or regioisomer is same as structural isomer. So it is also called constitutional or regioisomer. Okay, and actually stereo is we will also look into 6 different categories of structural isomers, and this stereoisomerism can actually be divided into two more branches. One is conformational and another is configurational. Okay, now as I talked about 6 more branches of uh, structural isomerism, I'll just list them out. We'll be talking in detail about each and every of them in some few seconds. So to start off with, this it is first is uh, chain isomer, second is position isomer, third is metamer, fourth is functional isomer, ring chain isomer, and finally we have tautomerism or tautomer. Okay, and in conformational actually we can divide it into two sub branches. We have amine inversion and we have rotation across sigma bond. Okay, and for configurational we have separate two branches or two more branches. One is geometrical and the other is optical. Okay, so let's start off with first with the structural isomerism part. So let me write the heading, structural isomerism. Okay, so in structural isomerism the molecular formula would remain the same. So let me write the properties of what is known as structural isomerism. So the properties are the same. Structural isomerism have same molecular formula, they have same degree of unsaturation, they have same dB, they have different IUPAC names, they have at least one of the physical or chemical properties that must be different. So they have at least one physical or chemical property that is unique as compared to the other structural isomers, or that is different, which is different than the rest. Okay, so now we'll be starting off with looking into the different categories of structural isomerism, and first we will pick up chain isomerism. First is chain isomerism. So what is chain isomerism? So if two or more isomers have different parent carbon chain, then they are known as chain isomerism. So if two or more isomers have different carbon chain, then different carbon chain or different carbon parent chain, different carbon parent chain, then they are known as chain isomers. So some examples of chain isomerism. So if we have simple pentane, so if we just change the positions of one of the carbon atom to have it located at a substituent on the second carbon atom, then the actual total number of carbon atoms in both the compounds are same, but only the parent carbon chain is getting different. In this case this was the parent carbon chain, and in this case this was the parent carbon chain. So the total number of carbon atoms in these two chains is changing, hence the parent carbon chain is changing. Okay, so let us look at the second type of isomerism or structural isomerism, which is positional merism. Positional isomerism. So in positional isomerism, if two or more isomers which has change in position of multiple bond or locands are nothing but substituents or functional groups, then they are known as positional isomers. Okay, so if two or more isomers have change in position of multiple bond or substituents or functional groups, etc., then they are known as positional isomers, but provided that the parent carbon chain remains the same. So this is an important point to notice here, that provided the parent carbon chain remains the same. What happens if the parent carbon chain changes? Then it would be an example of chain isomer, not positional isomer. So provided the parent carbon remains the same and the compound goes some of the changes like change in location of multiple bond, substituent or functional group, then it is known as positional isomer. Okay, so let's take some look into the examples of positional isomer. So we have a chain like this, and so what is the parent carbon chain here? Parent carbon chain here is this, and what is the parent carbon chain here? Parent carbon chain here is this. So what is the location of OH the same in both the cases? No. Here it is 1 degree, here it is 2 degree. Hence the location of the OH group changed from first carbon to second carbon. Hence it is an example of position isomer. Okay, let's take a look at another example wherein we change the position of pi bond. So the pi bond here was in between the first carbon atom and the second carbon atom, and here the position of pi bond is in between second carbon atom and third carbon atom. Hence the location of pi bond changed, hence it is an example of positional isomer. Let's look at some more examples. We have a cyclopentane ring substituted with 2 chloro groups and another cyclopentane ring substituted with 2 chloro groups. So here the position of chlorine atoms, the substituted chlorine atoms changed, and both of them are positional isomers of each other. So for your information, that this compound is known as geminal and this is called as vicinal. Okay, we'll look into these two later part of the course, but just for the information sake I am providing you this. Okay, so again, if we have 2 chloro atoms on the same carbon and 2 on different carbons but adjacent, this is also an example of position isomer, and its name is also geminal. I'm talking about the common name, and its name is vicinal. Okay, so let's talk about this example. We have so what is the parent carbon chain here? Parent carbon chain here is this one, and what is the parent carbon chain here? I suppose and I hope that you remember that the parent carbon chain starts from functional groups in case of carboxylic acid, aldehyde, ketone, ester, amide, acid halide. Okay, so the parent carbon chain starts from carbon atom of the carboxylic acid group. So this would be the parent carbon chain. Okay, and if this is the parent carbon chain, how many atoms were there in this parent carbon chain? Carbon atoms 4. And how many carbon atoms are there in this parent carbon chain? 3. So is it an example of positional isomerism? No. Why? Because the parent carbon chain is changing. Why? Because the number of carbon atoms in the parent carbon chain in both the two compounds are 4 and 3. Hence parent carbon chain is not remaining the same. That's why it is an example of chain isomerism and not positional isomerism. Okay, and similarly, if we have something like this and this, again in the same claim I can say that the number of atoms in parent carbon chain are reducing from 4 to 3 or are not the same in both the compounds. Hence it is an example of chain isomerism, not positional isomerism. Okay, let's look at this example. If we have nitrile group attached here and we have nitrile group here, what is the parent carbon chain here? Parent carbon chain is again changing, and the number of carbon atoms in the parent carbon chain is carbon chain is reducing from 4 to 3. Hence it is not an example of positional isomerism, because the condition of positional isomerism is the number of not the number of the parent carbon chain should remain the same in both the cases, but in this case the number of carbon atoms in the parent carbon chain is changing. Hence it is not an example of positional isomerism. So just to summarize it, I can write that aldehyde, carboxylic acid, amide, nitrile will not show positional isomerism. Okay, and this is only valid for monofunctional groups only. We'll talk about the corner cases more into our next lectures, but for now remember that this rule is applicable for monofunctional groups only. Okay, so with this I end this lecture. So in the next lecture we'll be taking on some more examples where you need to draw the positional isomerism of certain compounds. So till then, good luck and goodbye.